Flapping flight requires an explosive burst of muscular energy. It is the most intensive form of vertebrate locomotion. Yet, because of the high air speeds it allows, it yields a lower cost of transport per unit of distance than any form of terrestrial travel. This high-speed efficiency is what enables birds to undertake massive intercontinental migrations. But to achieve those distances, birds must operate at the extreme edge of metabolic optimization. To understand exactly where those evolutionary limits lie, aerodynamicists historically relied on theoretical mathematical models to predict the energetic costs of flight. Measuring the intersection of air physics and internal physiology allows us to map the precise energetic limits of sustainable flight. This graph illustrates the fundamental aerodynamic constraint on any flying organism. At very low speeds, the energy cost of developing lift, known as induced power, is extremely high. As the bird speeds up, that requirement drops rapidly. But speeding up introduces an opposing force: the energy required to fight drag. A combination of parasite and profile power scales exponentially as velocity increases. Summing these opposing forces produces the total theoretical power requirement for flight, a distinct U-shaped curve. The lowest trough on this curve is the minimum power speed. Flying at this exact velocity allows a bird to maximize its total time in the air for a given amount of energy. If the goal is to optimize fuel efficiency over long migratory distances, a bird needs to fly slightly faster. Drawing a tangent from the origin finds the maximum range speed, where the distance flown per unit of fuel is maximized. This aerodynamic model is mathematically sound, but it remains a purely theoretical framework until we can physically verify two things: the mechanical power output the bird generates and the metabolic power input required to sustain it. Measuring a bird's mechanical power output presents an immediate empirical challenge. We cannot measure force simply by watching wings flap. We have to measure the kinetic energy those wings transfer into the wake. To do this, researchers use particle image velocimetry in specialized wind tunnels, visualizing and quantifying the exact transfer of momentum through the air. These PIV images compare the wake topology of birds and bats. Birds use an inactive upstroke, folding their wings to minimize resistance, leaving a clean tail vortex. Bats generate a complex reversed vortex loop due to a slightly active upstroke. This PIV scan captures a hovering hummingbird, an extreme outlier to standard aerodynamics. It generates 25% of its weight support during the upstroke, maintaining bound circulation through the entire wing cycle, a massive biomechanical anomaly. PIV mapping captures the invisible footprint of force. It proves that different species have evolved vastly different mechanical solutions to navigate the constraints of the U-curve. Once we gather direct PIV and force sensor measurements, we can map them back onto the theoretical framework to see if reality matches the math. This plots muscle power output against velocity. For species like the cockatiel and dove, empirical data aligns perfectly with the predicted U-shape. But the magpie at the bottom produces a flat, L-shaped curve that completely violates the standard model. Deviations like this require intense morphological flexibility. The magpie morphs its wing profiles and changes its flight gaits mid-flight to bypass standard drag penalties. Because animals can actively morph their bodies to cheat aerodynamic models, measuring mechanical output isn't enough. To understand the true cost of flight, we have to measure the metabolic engine burning inside the bird. We need to shift our focus from the air outside the bird to the metabolic power input, which researchers track using isotopes like doubly labeled water. Converting mechanical output into a metabolic input is notoriously difficult, primarily because flight muscle efficiency varies significantly and scales positively with body mass. The solution is the Fick equation. This physiological model determines a bird's aerobic capacity and energy burn by calculating the rate of oxygen consumption. During intense flight, cardiac stroke volume and the blood oxygen extraction difference act as constants. Therefore, a bird's rate of oxygen consumption becomes overwhelmingly dictated by a single, trackable variable, its heart rate. Field researchers can implant tiny biotelemetry data loggers into birds, such as geese, to track their exact heart rates during free flight. This chart plots oxygen consumption and heart rate in geese. Notice the massive gap between the low-clustering walking data and the high-clustering flying data. Walking scales linearly with heart rate, but flying forces a much steeper quadratic relationship, a severe jump in metabolic cost. When plotting data across dozens of species performing primary locomotion, a generalized physiological rule emerged. Factoring in body and heart mass, oxygen consumption aligns almost perfectly with the square of the heart rate, providing a precise map of internal metabolic cost. Combining the external aerodynamic models with this internal metabolic data answers a critical question in avian ecology. What biologically limits the maximum size of a flying animal? The answer lies in a fatal divergence in scaling laws. As an animal gets larger, the required aerodynamic power scales aggressively upward at a power of 1.17, but the available muscle power to sustain that flight scales at a much shallower rate of 0.67. We can see the consequences of this divergence by looking at the power curves of a highly aerobic small bird next to a soaring giant. Hummingbirds possess a massive physiological safety margin. Their maximum sustainable power sits far above the required aerodynamic U-curve, allowing them to hover effortlessly. But as body mass increases, allometry acts as a vice. The condor's maximum available power barely clears the very bottom of its U-curve, permanently stripping it of the ability to sustain continuous flapping flight. This allometric vice eventually creates an absolute mathematical ceiling, where powered vertebrate flight becomes physically impossible. This graph plots wing flapping frequency against body mass. By analyzing these kinematics across different species, researchers can pinpoint the exact intersection of failure. Both the fast and slow flapping capabilities of birds follow a downward trajectory as body mass increases, forcing the regression lines toward a singular point. They mathematically intersect at roughly 41 kilograms, corresponding to a 5.1-meter wingspan. Beyond this mass, no vertebrate can physically generate enough muscle power to sustain horizontal flapping flight. Every species in the sky operates within the narrow margins allowed by the unyielding physics of the U-curve and the allometric scaling of the heart.